Here's an example. A car traveling at a speed of 20 meters per second rounds a flat curve whose radius is 175 meters. A. Draw a side view free body diagram for the car and indicate the direction of the acceleration. B. Use that free body diagram to set up the equations needed to determine the frictional force acting on the car. And then C. Solve those equations for the coefficient of friction between the tires and the road. Alright, so here is the side view free body diagram for the car, and in this drawing, this car is driving straight towards us. So its little tires are here, here's the headlights, and the windshield. It's driving straight at us. So there's a normal force up, mg down, and the force of friction is pointing towards the center of the circle. The free body diagram shows the car coming out of the page and rounding a curve to its left, or your right. So it's going to round the curve like that. The normal force and mg are equal, as we assume the car is not bouncing up and down on the road. The force of friction provides the centripetal force that enables the car to round a flat curve, which is part of a circle. We can first find the normal force by analyzing the y direction. So we have F equals ma, there's Fn up, mg down, there's no acceleration up or down, so that's 0, therefore the normal force equals mg. Then we go to the x direction, we only have that one horizontal force, the force of friction, and we set that equal to ma. A is v squared over r, since we're driving in a circle, and the formula for friction is mu times the normal force. Alright, then we just pick up where we left off on the last slide. Mu times the normal force equals mv squared over r. We solved on the previous slide for the normal force, which was mg, so we're going to substitute that in right there. Then we can go ahead and cancel those m's. Then we have mu g equals v squared over r. We're solving for the coefficient of friction, so we're going to solve for mu, divide both sides by g, and we get mu equals v squared over r times g, or g times r. Then we go ahead and plug in our numbers, and we get 0.23. And generally, coefficients of friction are smaller than 1, so this answer is plausible.
Example 2, flat horizontal curve. The driver replaces the tires that had a coefficient of friction of 0.23 with new tires with mu equals 0.50. How does this affect the maximum speed that the car can safely achieve on the curve? We'll start by listing the givens, and we have the same radius of curvature here, 175 meters. We have a new coefficient of friction. So we're going to take advantage of the free body diagram and equations from the previous example and use the new coefficient of friction to find the maximum speed. So here we have from the previous slide, mu g equals v squared max over r. We want to solve that for v max. So we multiply both sides by r. Then we switch around the equation, so we put v squared on the left, take the square root of both sides, and we now have our algebraic expression. And the nice thing about this, we've already done the algebra, so we can change the coefficient of friction and the radius of the curve to whatever we want. But in this case, we have 0.50. Here's gravity, that of course stays the same, and here's the same radius of curvature. We get a maximum speed of 29 meters per second. So the new tires allow the car to stay safely on the curve at 29 meters per second, which is greater than the 20 meters per second achieved with mu equals 0.23.